and welcome to the Volta Foundation webinar series, where battery industry experts delve into trending topics. Today, we have an incredible global team joining us from Thermo Fisher Scientific, and they're here to share insights on advanced analytical technologies. My name is Myra, and I'm the Director of Member Success at Volta Foundation. Thanks to everyone for joining in today. If this is your first time joining a Volta Foundation program, welcome officially to the largest network of battery professionals globally. Over 75,000 professionals, actually. Our webinar series is one of about 15 programs organized by Volta Foundation, which is a nonprofit organization dedicated to supporting the growth of the battery industry. We've hosted over 50 in-person and virtual events just within the last year. We produce industry-leading publications like the Annual Battery Report, which was recently released digitally. PDF is coming soon. We host the largest virtual battery career fair event within the industry. We host industry-leading programs, Women in Batteries Conference, produce networking and continued education programs such as Battery Forum, Battery Socials, and Battery Bits, as well as webinars. And everything we do is open access and centered on helping companies and professionals like you connect, collaborate, and advance your businesses and careers. In addition to today's program, a couple of things might show up in the chat here. Be sure to check out Battery Street, which is Volta Foundation's Slack channel and the largest open communication platform within the industry. So a really great place if you have questions, you want to connect, attending events, and want to get together with fellow battery industry experts. You can view past programs, both Battery Forum, Women in Batteries, and webinars on Volta Foundation's YouTube channel. And be sure to subscribe to our newsletters on LinkedIn just to stay up to date on trending news and thought leadership. All right, now that everyone is up to speed on Volta Foundation, we'll chat logistics. For the audience, if you haven't attended one of our programs today, just a reminder, you can submit questions throughout the program in the chat function throughout the event. Enter them there, and the team will come back on after the content presentation and answer as many as possible. So even if they don't get to it today, they will be aware that questions have been asked, so they'll be able to follow up after the program. If it's platform related, myself, Dana Bubanovich, Volta Foundation staffer in the background, will help out where we can. And bonus, really great feature for today's program. The Thermo Fisher team has included incredible resources in the resources section, including a PDF of the slides for today, as well as just amazing links, on-demand webinars, resources, all discussing advanced analytical technologies that they'll cover today. So, all right, all caught up on Volta Foundation. We're caught up on the background details. As a medical engineer, I'm really excited to hear about advances in analytical technologies. So, Kyle, I'm going to hand it off to you for today's discussion.
Thank you, Myra.
Thanks.
And also thank you to the Volta Foundation for hosting today's webinar, where we'll be sharing with you advances in technologies for battery electrode mixing, composition analysis, and defect detection. Scientists worldwide trust Thermo Fisher Scientific to help them accelerate their research and enhance their productivity. We provide a combination of innovative technologies, purchasing convenience, and comprehensive support. At Thermo Fisher Scientific, our company mission underpins everything that we do. We strive to enable our customers to make the world healthier, cleaner, and safer. We see the development of batteries as an essential tool in making the world both cleaner and safer. Cleaner through the adoption of electric vehicles and renewable energy, and safer through the benefits that energy independence brings as countries decouple from carbon-based energy sources. Today we'll learn 3 workflows that battery companies are utilizing to manufacture high-quality, high-performance batteries. On the next slide, we'll see today's agenda. So I'll welcome my colleagues. First today we'll hear from my colleague Annika about tools that improve the mixing quality of active electrode materials. Next we'll pass to my colleague Janam and we'll hear about new process Raman analytical capabilities that can monitor the composition of battery materials and slurries to ensure they are consistently within control limits during the manufacturing process. Finally, we'll hear from my colleague Alon. He'll be telling us about a new and advanced metrology that's helping battery manufacturers ensure their coated electrodes are correct in terms of thickness and free of defects. So Thermo Fisher Scientific serves the entire battery value chain with advanced analytical technologies from the research environment through to recycling. We lead the market with tools such as spectroscopy, electron microscopy, and mass spectrometry. Today, we'll learn about 3 technologies that enable battery manufacturers within the electrode production phase. This manufacturing stage accounts for approximately half of the cost and scrappage of the entire manufacturing process. So here, improvements to the process are critical in terms of productivity. So I'll now pass to my colleague Annika to hear about the first of our 3 technologies that are improving production outcomes for battery manufacturers across the globe. Thank you, Annika.
Yeah, hi, my name is Annika Völp. I'm an application specialist for extrusion at Thermo Fisher Scientific, and I present in the next 50 minutes how twin screw mixing advances the battery manufacturing and research. I start with presenting twin screw technology on the first slide. Yeah, in general, the task of the parallel twin screw extruder is to apply thermal and mechanical energy to create a dispersion and shape it. Solid materials such as the anode or cathode active material and carbon black are fed into the extruder barrel and sheared. During melt extrusion, a polymeric binder is added, which is melted in the heated twin screw barrel. In wet extrusion, solvents and binders are added to the barrel via a liquid feeding system. All materials are mixed, sheared, and compacted and pushed through a die. The parameters to be controlled include material feed rates, screw speed, and the temperatures of the various barrel zones at the die. These settings influence the measurable parameters such as the material temperature and the pressure in the die, as well as the screw torque and the material residence time. An important process parameter is the specific mechanical energy input, or SME, which is calculated from the power required for the mixing or the torque that applies to the screws. With a die attached, the material can be formed into pellets or sheets if its viscosity allows. This applies for semi-dry electrode processing, but most often electrode slurries are required. For mixing those, no die is needed, as presented on the following slide. Because extrusion is defined as shaping material by pushing it through a die, we speak of a twin screw mixer then when no die applies. With such a twin screw mixing setup, battery materials can be mixed with and without the use of solvents. The mechanical and the thermal energy input in the material is defined by the screw design, the screw speed, the feed rates, and the mixer temperature. No pressure is applied to the material. It is conveyed without any constriction out of the mixer and collected in a container. Twin screw mixers can be applied at several points in the battery manufacturing workflow, as shown on the next slide. So, for example, for compounding electrode active materials, twin screw mixers can be used, for example, for granulating silicon anode materials and fully solvent-free cathode materials. They are also used in the process of dry electrodes. Separator film production. Conventionally, separator films are produced by extrusion, and it's a well-developed process. But for novel battery concepts such as solid-state batteries and gel polymer separators, lab-scale twin screw extruders are particularly beneficial. For electrode manufacturing, twin screw mixers enable the continuous mixing of cathode or anode slurries, and this offers a beneficial alternative to batch mode mixing, typically done with planetary mixers. In manufacturing, the twin screw mixers provide the following benefits over planetary mixers. The reproducibility is better. Twin screw mixers ensure there are no batch-to-batch variations, enhancing the consistency of the production process. There's less need for manual operation, reducing the impact of the individual operator handling. The higher shear forces in the twin screw mixers lead to superior dispersion quality. This results in fewer screen changes and less blockage of the downstream filters before the coater. The process also introduces fewer impurities, significantly reducing the presence of unwanted particles in the slurries. Twin screw mixers require less physical space, offering a reduced footprint. They also demand less cleaning and maintenance, saving both time and labor. Material effectiveness is enhanced. The mixing process is significantly faster with twin screw mixers, completing the task rather in minutes than hours. Continuous processing minimizes then the material losses, making the process more efficient. Twin screw mixers are also effective for large-scale dry processing, which we talk about later. Twin screw mixers provide good scalability due to the large surface to volume ratio in the mixer, making it easy to transition from lab scale experiments to full production. High material and time consumption in manufacturing scale create the need for lab-scale twin screw mixers for advancing battery R&D. A downscaled solution is presented now on the following slide. Lab-scale twin screw mixers are essential for developing and testing new battery materials efficiently. They also allow researchers to optimize formulations with small quantities before scaling it up. Here you see the Energy 11 twin screw mixer. The Energy 11 features a patented design that prevents dust entry, ideal in research and pilot scale environments. It includes a detachable touchscreen. It has 7 adjustable heating zones, an integrated data visualization, and exchangeable contact parts for easy cleaning and preventing cross-contamination. The split barrel design allows for faster cleaning and quick material switches. It also enables observations of the material along the screw after an abrupt stop, providing valuable insights. Exchangeable barrels prevent cross-contamination by using dedicated barrels for specific materials, like one for the anode and one for the cathode mixing. Lab-scale extruders, like those from Thermo Fisher Scientific, are designed for small quantities and confined spaces like glove boxes. They are essential for sensitive battery material requiring a dry or an inert atmosphere, but also ensuring the operator safety from toxic solvents and powders. Segmented screw design and multiple feed ports make twin screw extruders ideal for R&D. The screw configuration and dosing positions can be adjusted quickly for precise control. And unlike dissolvers and centrifugal mixers, these extruders offer more parameters to manipulate, enhancing then the optimization. Available screw elements to design a screw configuration are shown on the next slide. Here you see screw elements like the discharge element that increases the pressure at the die entry here on the left, conveying elements with various lengths and conveying directions, distributive mixing elements that mix with minimum shear, and dispersive mixing elements that apply increasing shear force with increasing offset angle when arranged in mixing blocks. Those elements are arranged like beads on a string to fulfill a specific series of processing units. An example for this is shown on the next slide. This screw design of a parallel twin screw mixer is an example from polymer processing, and here it determines the material processing units from right to left. Powders are fed into the main feed onto the elements with a wide screw gap. This zone is cooled that the powder does not melt and block the port. In the next barrel zones, a temperature profile is set to melt the material and control its viscosity. Next, there is a zone with conveying elements. Optionally, liquids may be fed into this zone. The first kneading zone plasticizes the material by shearing. A second conveying zone allows for secondary powder feeding. The next compounding zone mixes all materials. And in the third conveying zone, gases could be removed by venting the barrel. Finally, the pressure is built up and the material is pushed through the die. The screw design is specific to the material and the unit operations that the material is supposed to undergo. Some battery mixing applications can be realized with the appropriate twin screw mixer designs, and they are highlighted on the next slide. Here you see the variety of morphologies that the battery materials can be produced with a twin screw extruder as electrode slurries, dry mixed electrodes, semi-dry films, and solid-state electrolytes. Next, we want to focus on twin screw slurry mixing. Let's dive into electrode slurry mixing and the impact of the screw design. De-agglomeration of carbon black is a significant challenge in the mixing of the electrode slurries. Through simulations of a digital twin and experience with 3 different kneading section designs, shown here on the top, 2 different throughput rates, 4 screw speeds, a correlation was found between process parameters and the particle distribution of the anode paste. In the left graph, you see the particle size distribution in anode slurries mixed with the different screw designs and different screw speed. The dispersion index can be calculated from the median of the carbon black fraction from the size distribution. The higher it is, the smaller are the carbon black agglomerates. The specific feed load is the volumetric throughput divided by the screw speed and the screw diameter cubed. The left graph shows a good correlation of the dispersion index with the reciprocal feed load and a decrease in carbon black deagglomeration with increasing screw speed. Therefore, the specific feed load provides a good basis for scaling anode slurry mixing, assuring consistent carbon black deagglomeration. On the next slide, we see the screw speed impact on carbon black deagglomeration in SEM images. These SEM images of graphite anodes mixed with a twin screw mixer at 120 RPM and 900 RPM screw speed respectively show carbon black agglomerates on the larger graphite particle flakes. Higher screw speed and thereby higher shear impact result here in a higher amount of smaller carbon black agglomerates. Next, we see the screw speed impact on another material. Here you see an LFP cathode. The LFP size distribution was widened and decreased because this screw design led to breakage of the LFP particles. The effect increases with higher screw speed due to higher shear, and it's probably not a wanted effect. These 2 examples show that the screw design and the speed needs to be adapted to the specific materials. When a suitable screw and a process design is developed at the end, the next step is to scale it up. Some guidance is given now in the next slide. We can effectively transfer the knowledge from lab to production, ensuring process consistency and maintaining product quality if we follow some rules. To ensure consistency, we must use the same screw design in both lab and production environments. It is crucial to maintain a constant ratio of the length of the screw, L, to the outer screw diameter, DO, ensuring similar mixing and melting behavior. The ratio of the screw outer to inner diameter should remain constant. It ensures the same filling conditions in the voids of the screws. Keeping the ratio between screw to barrel distance and screw outer diameter constant is essential. This helps in achieving the same shear rate at the same screw speed. Then we should use the same screw speed in both settings to maintain the same mixing intensity. Maintaining the same steel temperature is important to ensure thermal consistency throughout the process. But have in mind that the heating surface to volume ratio drops in decreasing with decreasing screw diameter, as shown here in the graph on the right. A simple law to scale up the throughput is then to keep the specific feed load constant. If that is done, the throughput can further be adjusted to obtain the same specific mechanical energy, which is a measure of the energy input into the material per unit mass. Therefore, you can change the throughput to achieve the same torque. However, in wet slurry processing, it is most often so low that keeping the specific feed load constant is usually sufficient. If you can measure the material residence time, it should remain the same to ensure similar processing conditions and material properties. The melt temperature should also be consistent between lab and production to maintain the same material thermal history. By adhering to these principles, the material's experience within the process should be the same, ensuring process consistency and maintaining product quality. On the next slide, the different sizes of Thermo Fisher Scientific twin screw mixers are presented. The smallest is the tabletop Energy 11 with 11 millimeter screw diameter. Besides that, also larger twin screw mixers with 16 millimeter and 24 millimeter screw diameters are available. This portfolio covers a material throughput range from 100 milliliter per hour to up to 20 liter for battery slurries. Unlike production scale twin screw mixers, they are easily operated by just one person and require very small sample volumes and are scalable to larger sizes. These features enable to save time and money on application testing, develop products and test materials at small scale, and to gain process experience and train operators for large-scale machines. The image on the upper right shows the equal material flow velocity simulated for all of these three sizes, and this gives a glimpse into a submitted publication on scaling continuous battery slurry production. Now let's have a look onto dry processing in the next slide. The conventional manufacturing of lithium-ion battery electrodes involve mixing active materials and additives with a solvent to create a slurry, coating it onto a current collector foil, drying, calendering it to the desired density and height, and laser slitting the electrodes. Twin screw mixers offer the potential to mix electrode materials with binders and additives using little or no solvent due to higher shear energy input. The mixed material can be directly fed into a roller press and calendared onto the current collector foil without drying. This saves a lot of energy. Suitable binder formulations like PTFE or PVDF allow the dry cathode granulate mix to be calendared directly onto the current collector foil. PTFE forms fibrils under shear to bind the particles, but the shear must be controlled for proper fibrillation. Sheet extrusion of the electrode material is also possible, providing more uniform dosage of the calender, but it requires about 20% of solvent. Twin screw mixing reduces solvent use, energy, drying costs, and saves space by eliminating the drying line. However, dry electrode processing remains at pilot scale due to challenges in calendering and scale-up. The next slide discusses a study on screw design for dry processing. The screw design determines the specific energy input applied to the material. Here you see two screw designs with 5 mixing blocks and one without any mixing blocks. Below are SEM images of LFP cathode material mixed with PTFE using the two screw designs. The left SEM image shows the cathode mixed with 5 kneading blocks. The PTFE fibrils are small and well distributed. The right SEM image shows the cathode mixed without kneading blocks. The PTFE fibrils are much larger because the mixing here relies only on particle-particle interactions, and the lower energy input is insufficient to evenly disperse the PTFE. However, now let's examine the cycling capacity of half cells made from these materials compared to a wet cathode mixed in a planetary mixer as a reference, shown in the graph on the right. The cathode mix without kneading blocks in blue exhibits the highest capacity at all cycling rates over 40 cycles. The cathode mix with 5 kneading blocks in black has the lowest capacity and cycling stability. This study suggests that the PTFE fibrils in the strongly sheared sample isolate the conductive pathways leading to inactivation of the LFP. This highlights the importance of tailoring the screw design to provide the right energy input for the specific PTFE grade. And this brings us to the summary of the presentation on twin screw mixing for processing dry electrodes. I would like to highlight the following points. In manufacturing, twin screw mixers allow for the modification of shear effects by adjusting the screw design and processing parameters such as screw speed, temperature, and material throughput. When applied for continuous wet and dry electrode paste mixing, they provide great processing flexibility and quality consistency to achieve a superior carbon black deagglomeration and dispersion and good PTFE fibrillation and binder distribution. Continuous mixing also leads to high quality consistency, reduced downtime, and less cleaning effort. Twin screw mixers are easier to scale compared to planetary mixers or dissolvers. Lab-scale twin screw mixers offer scalable mixing technology for the development of formulations and screw designs with small sample quantity and minimal space consumption in glove boxes or dry rooms. To find out more, please visit thermofisher.com/battery-extrusion. With this said, I hand over to Janan now.
Hello, everyone. My name is Janam Pandya, and I'm an application scientist for spectroscopy at Thermo Fisher Scientific, specializing in Raman spectroscopy. I have been working with the Raman spectroscopic technique for about 10 years now, and today I'm very excited to share with you a novel and emerging approach utilizing Raman spectroscopy for real-time process monitoring in battery industry through the next few slides. So first of all, what is Raman spectroscopy? Raman spectroscopy is a vibrational spectroscopy technique invented in 1930 by an Indian physicist, Dr. C.V. Raman. In simple words, it is a light scattering technique, meaning the sample of an interest is shined with a visible laser of specific wavelength. And as the light interacts with the sample, most scatters elastically with the same energy as the incident light. However, there will always be some light that will scatter inelastically, meaning with different energy than incident light. This happens due to the vibration of the molecular bonds present in the sample, which is called Raman scattering. When the scattered light enters the instrument, a filter filters out most of the light except the Raman scattered photons, and the detector then detects and plots a Raman spectra for a particular sample, which is often called Raman fingerprint due to its selectivity and specificity in providing information. The peak position on the x-axis provides information on the molecular bond present in the sample, which helps in identifying the presence of an analyte, while the intensity of the peak on y-axis, or area under the peak, just like HPLC, can be directly correlated with the concentration of the sample. So what are some of the advantages of Raman spectroscopy? Let's look at that on the next slide. One of the biggest advantages of Raman spectroscopy is that it is extremely fast and usually provides results in milliseconds to seconds. It is also a non-destructive technique and requires no sample preparation, unlike some of the other analytical techniques, making it suitable for in-process monitoring. Depending upon the optics used, it can be used to measure the sample through the containers and packaging materials, such as glass and plastics. It is also extremely data rich as well. Additionally, Raman spectroscopy can provide quantitative and qualitative information and can measure multiple analytes with single scan. What types of samples can you measure with Raman spectroscopy, you may ask? Pretty much all. Solids, gels, liquids, gases, powders, slurries, and more. This makes Raman spectroscopy desirable in multiple applications, which we will look at next. Raman spectroscopy has already been utilized as an inline process monitoring tool in many industries such as oil and gas, chemicals, biopharma, and polymers. However, it is rapidly gaining traction in new markets such as clean energy application, hydrogen liquefaction, sustainable aviation fuel, and battery industry is definitely one of them. So how does the Raman instrument look like, and how do you utilize that for in-process monitoring in battery manufacturing process? We will look at that in the following slides. Raman instruments have gotten really compact in recent years, and the analyzer that Thermo Fisher Scientific offers, which is MarkMetrix all-in-one process Raman analyzer, is one of the smallest process Raman analyzers, about the size of a laptop, and requires no calibration, which can be easily moved or mounted in the manufacturing facility. The laser is transmitted from the instrument to the sample via fiber optics cable, which is then connected to various types of patented optics. I have listed some of the commonly utilized optics in the battery manufacturing processes here. Process ball probe is contact probe manufactured using Hastelloy material, which can withstand corrosive and oxidative chemicals in environment. It can be utilized to measure slurries, liquids, and powder sample, and can withstand high temperatures and pressures. The threaded process probe is specifically designed to fit in the extruder, either on the die end or mid-barrel. It can also withstand high temperatures and pressure, and is commonly utilized to monitor extruded uniformity or to monitor reactive extrusion. The flow cell ball probe is commonly used for gaseous and liquid samples, including electrolytes, and can measure dynamically moving or flowing samples. On the other hand, the non-contact probe is typically utilized for non-contact application at a distance. For example, to characterize electrode surface or to measure moving samples on a conveyor belt. In the next few upcoming slides, I will discuss some of the battery-specific applications in detail. As most of you might be familiar with, there are 5 basic steps in battery manufacturing, including material preparation, electrode manufacturing, cell assembly, forming, and recycling. In each of these 5 steps, process Raman can play vital role in providing inline measurements of key quality attributes, thereby saving time, money, and resources. Let's look at some of those examples in the next slide. Process Raman can provide real-time information in characterizing the cathode and anode material, as well as quantifying the active material concentrations. On the other hand, electrolytes are often strong Raman active materials, and process Raman can be utilized in quantifying different electrolyte components in real time using during the formulation, and flow cell will be an ideal choice here. The traditional measurement techniques often requires sampling of and offline analysis, which could be hazardous and unsafe. Process Raman equipped with corrosion-resistant probe or a flow cell could provide accurate inline on-demand measurement. The next slide shows the Raman signature of an example cathode material. The spectra on the left-hand side of the screen shows the Raman fingerprint of lithium carbonate, which is used as a raw material in LFP and LCO manufacturing process. During the synthesis process of lithium carbonate, the lithium carbonate can be differentiated from dissolved carbonates and can be quantified due to the distinct peak as shown by orange spectra on the figure on the right-hand side. Moving to the next slide. Process Raman can also be instrumental in active material mixing process, whether it is stirred tank mixing or mixing via extrusion process. For the stirred tank mixing process, the process ball probe with hastelloid construction can be used for continuous insight into the mixing homogeneity. Whereas in the extrusion process, a specifically designed threaded process ball probe can be used for in-extruder assessment of material structure, concentration, as well as homogeneity. Such inline measurements of the extrusion process can provide powerful insight into material characterization, distribution of binder, and allow the better process control and improving overall product quality. But can Raman really characterize different materials? Let's look at that in the next slide. Process Raman can be utilized for both anode and cathode material characterization, as shown in the top left figure. Raman can differentiate between both graphene and graphite structure of carbon. Beyond that, the technology can even further classify single versus multi-layers, as well as ordered or disordered carbon materials. The combination of peak position, peak heights, peak shape, and peak ratio can be utilized to characterize such different properties of anode material. Moving on to the next slide, cathode material can also be characterized using process Raman. As shown in the figure here, each of the different active cathode material, including LFP and NMC, indicate distinct Raman signature. The intensity of these peaks on the y-axis can be utilized for the quantification and identifying the homogeneity of the materials during the mixing and forming process. Last but not the least, on the next slide, process Raman can be also important tool during electrolyte filling process as well as material recycling. It can provide real-time information about the electrolyte distribution throughout the electrode and if there are any imbalances and gradients exist. A homogeneous distribution of electrolyte is extremely important for good battery performance. In recycling operation, a process Raman can be utilized for real-time monitoring of electrolyte and solvent concentration during the removal process, as well as for quantifying active material concentration post-separation step. On the next slide, I would like to summarize what we just talked about today. So in summary, process Raman can be a powerful tool in providing valuable insight throughout the battery manufacturing process. It is a non-destructive tool that eliminates the hazardous sampling need and can provide measurements with within seconds or milliseconds, and in turn, helping in reducing downtime while maximizing the resources and improving the overall product quality. If you'd like to learn more about the process Raman analyzer that Thermo Fisher Scientific offers, please visit www.thermofisher.com/markmetricsAIO. Thank you so much for your time today. Now I would like to turn to my colleague, Alon, who would talk about recent advancement in electrode coating, metrology, and inspections. Thank you.
Thank you very much, Janan. My name is Alon Weissman, and I'm a Senior Manager of Strategic Business Development in our Production Process and Analytics business unit. The importance of ensuring optimal mixing performance and correct flowability of active materials, slurries, and powders can hardly be overstated. Manufacturing electrodes at mass production scale and with quality required by the end users seems to be one of the most challenging tasks the industry is facing today. Research suggests that the largest losses of production yield are related to quality issues in slurry mixing and electrode coating processes. This is especially important for companies looking to enter the market and rapidly scale their production to meet the volumes and the stringent quality requirements of the automotive industry. Ensuring the uniformity of the active material loading during the electrode coating process is one of the most critical quality parameters. When the anode and the cathode come together in the assembled cell, the ratio of anode to cathode charge capacity, A to C ratio or N to P ratio, will determine the electrochemical balance and will affect the performance of the cell. Anode to cathode balance needs to be maintained locally in each point over the entire electrode area, not just as an average. An incorrect N to P ratio can speed up capacity decay and reduce lifetime of the cell. It can promote formation of dendrites, hotspots, and in extreme cases lead to a thermal runaway. Close monitoring and tight control over the active material loading uniformity is of increasing importance, but until recently, the tools available to process engineers and quality teams for measuring the electrode loading were limited to single point or scanning sensors. As the battery technology continues to develop, so does the need for more advanced metrology tools. Conventional single-point sensors only interact with a small fraction of the surface of the electrode, usually less than 5%. Variations in loading on the edges of the coating are difficult to measure, and the time it takes to collect data for representing a loading profile is measured in multiple seconds, slowing down the ability to respond to process changes. Data available for traceability and failure analysis is also limited to the same small fraction of the product, resulting in potentially non-conforming areas of the electrode, making it into the downstream process and resulting in costly scrap of a complete cell. A new technology introduced by Thermo Fisher last year aims to address these challenges. This new technique, called inline mass profilometry, measures the loading on the entire electrode during the coating process. It captures a complete side-to-side loading profile every millisecond and delivers complete mapping of the entire electrode at full production speeds. To help visualize the difference between the conventional single-point scanning gauges and the mass profilometer, we can use the illustration on this slide. A scanning gauge usually consists of a frame on which a sensor moves from one side of the electrode foil to the other and repeats. The resulting dataset captures sort of a zigzag pattern across the electrode as the coated foil moves through the process. For example, if the line speed is 60 meters per minute and the sensor takes 5 seconds to move left to right, 5 meters of product would have passed until one single profile measurement is completed by the scanning gauge. Areas that do not pass under the sensor are not analyzed at all, and the coating variations or defect could easily be missed. Mass profilometry, on the other hand, captures a complete side-to-side loading profile nearly instantaneously every millisecond. Operating continuously, it produces a record of the entire electrode row and makes the information and the results available in real time to help make process decisions and monitor quality. Mapping the active material loading on the entire electrode enables one to get a better understanding of the coating process performance. Edge features are analyzed in greater detail, and it becomes possible to identify spot defects like streaks, divots, and high and low loading regions. The example screenshot here from the mass profilometer HMI shows two patches of NMC cathode. This data was collected at 60 meters per minute line speed. Mass profilometry data makes it easy for the operator to see that the loading is high and out of spec in the bottom right section of the lower patch. A closer look also reveals what appears to be a streak in the machine direction. The software is able to calculate statistical variables like average, maximum, and minimum loading in grams per square meter, and transmit this information in real time to the plant control system. Special features enable the user to focus on multiple areas of interest, like the patch edges, for example, and easily identify and trace non-conforming areas to a specific position on the roll. The example in this slide is a good way to consider the difference between optical inspection and mass profilometry. Image from an optical inspection system on the left looks at the surface of the electrode, and in this case, the algorithm did not flag any abnormalities. Mass profilometry mapping of the same sample shows clearly that the darker areas in the image are actually areas where the loading is too high, indicated in red. Additionally, the vertical streak of high loading, most likely resulting from an incorrect adjustment of the die bolt in the coater machine, is clearly identified by the mass profilometer, while it is completely invisible to the vision inspection system. To emphasize the unique capability of mass profilometry for detection of loading defects, we performed an experiment where a sample of electrode was measured and the mapping of it is shown on the left. We then took a few flakes of the same cathode material and placed them on top of the sample. You can see these flakes in the middle. They range in size from approximately 1 to 5 millimeters. We then remeasured the sample with the flakes on. Looking at the photo of the electrode on top, you can see larger flakes with some effort. The smaller flakes are much harder to see. They're nearly invisible. There is no color contrast, and the optical inspection system would struggle to detect this type of a defect. The mass profilometry data, however, makes the flakes easily detectable. The difference in mass in the local area where the flake is placed is very large, and it is easily picked by the system. Being able to analyze the distribution of active material on the entire electrode as it is being coated gives one the ability to make quick adjustments and tune the coating process on the fly. The example here shows a variation in loading between the left and right sides of the patch. You can also see small vertical streaks that are actually visible in the photo of the same patch on the right, if you look closely at the light reflection on the top and bottom of the central area. With this information available on the fly, the ability to tune the process as it is running is valuable, and it helps speed up parameterization and validation workflows. In addition, one should consider the value of reducing the amount and cost of scrap that is produced during startup activities and the initial process qualification. In the example here, the operator makes a change to the process to correct the low loading region, but in doing so, they create a problem on the edges of the patch where the loading becomes too high. Without an in-process analyzer capable of detecting these variations, the user would have to rely on laboratory sample tests that can take many hours and result in production of a large amount of out-of-spec material. Using a mass profilometer as an analytical tool in battery electrode coating process enables one to capture and map the loading of active material on the entire roll and correlate the loading information to a specific location on the roll with every measurement point stored with its XY position. This information helps you understand the behavior of the coating process, see the shape of the cross direction and machine direction loading profiles, and better control the uniformity of the coating process across the entire coated area. Key statistical variables are calculated, trended, and reported in real time. If loading defects occur, they are recorded and the operator can scroll through the data to see what has happened and where. So out-of-spec parts of the roll can be segregated early before they cause failures during the end-of-line testing and result in costly scrap of a complete cell. Operating at full production speed, a mass profilometer generates a lot of data. Especially during process qualification, one might want to keep a full record and be able to examine the effects of changing mixer or coater parameters. The system is able to store a couple of weeks' worth of data on its onboard storage when operating 24/7 continuously. One can also configure a REST API client to pull specific data into the plant archiving system, or use another industrial protocol like OPC for real-time data exchange with a plant control system or a PLC. If you're coating in a pattern, the software can automatically identify individual patches and includes tools to help you analyze and report the data, greatly improving the traceability of production and giving the user a greater confidence in the quality of each individual patch of electrode. I will spend a few moments on the integration of mass profilometers into electrode production lines. The platform is a modular one and allows the user to configure one or more analyzers in a synchronized system for various coating line configuration in wet or dry electrode production. In addition to being used for inline metrology, the system can be equipped with an offline sample stage and used for testing discrete samples at line or in the laboratory. To summarize this section, as the technology for battery manufacturing continues to develop, so do the production and analytical tools. The new inline mass profilometry technology enables greater process understanding and continuous inline quality assurance to help battery manufacturers reduce cost and have greater confidence in the quality of their products. Lastly, to reflect on the broader value of partnering with Thermo Fisher for your technology needs. As the global leader in serving science, we operate in 170 territories with over 140,000 colleagues, generating over $40 billion of revenue. We innovate, reinvesting almost $1.5 billion annually in research and development of new products. We serve the battery value chain with advanced analytics from research to recycling, with market-leading technologies in spectroscopy, electron microscopy, and mass spectrometry, as well as compounding and rheology and process analytical tools like mass profilometers. To find out more about our solutions, visit our website on thermofisher.com for battery solutions and join our battery industry community. Thank you very much for tuning into our presentation today. We hope that you found the content engaging and useful. We will now ask you to respond to a short polling question before moving to the Q&A. You should now see a pop-up window on your screen. The response allows multiple options. Please select all that apply. We will give it a few more seconds as the responses are coming in.
I love it. Thank you so much, Thermo Fisher team. So as we have the poll up, this is amazing. We have some great questions coming up. So I think maybe we bring the full team back out. Yeah,
I'll
hand it over to Kyle. Thank you guys so much. All right. If you guys, for the audience, if you didn't get a chance to enter your question in across the various technologies that were discussed today, enter them into the chat. Kyle's reviewing, and they'll answer them now. Thank you guys so much.
Well, firstly, thank you for so many questions. We certainly have a lot to choose from. So we're going to start with some. I'm going to pass to my colleague Janam for the first couple. So in your presentation, you shared the Raman tool. Does Thermo Fisher offer Raman sample holders for air-sensitive material, Janam?
Yes. Thanks, Kyle. Yes, so Thermo Fisher does offer sample holders for the non-contact probes. So the samples can be placed inside that chamber, and then the probe can be inserted from its side, and the top can be closed with a cap that allows for air-sensitive samples to be measured that way. If you opt for a contact probe, the contact probe can also be introduced in your existing airtight environmental container and can be sealed for continuous measurement in the particular container that you have.
Great stuff. And staying with you, Janam, there's another question here. What are the safety considerations when using the Raman spectrometer? Will the user need to implement laser safety programs to use the tool?
That is a great question. So the spectrometer itself provides various safety features to facilitate the laser safety, and that includes the keys that allows you to operate or shut off the laser operation. It comes with automatic interlocks, which can be triggered at a specified condition. Like, for example, let's say you say the door, as soon as the door opens, it will kill or shut off the laser. So there could be automatic controls placed in that way. There are controls on enabling or disabling lasers in the software, as well as the spectrometer. We also provide laser safety glasses for added safety as well. So there are many different laser safety considerations that we have considered designing this instrument.
Awesome. Thanks, Janam. I'm going to come to you next, Annika. So is it possible to use a twin screw extruder for reducing active material particle size? If yes, what is the minimum particle size that could be produced?
Actually, yes, but usually is not a desired effect. There are even some suppliers of materials that tailor their active material to not be crushed in an extruder or a twin screw mixer. However, that's possible depending on the parameters that you choose and the screw design. I can only answer that question for carbon black because there I did the investigation in size reduction, and there you reduce the size from 1 micrometer down to 100 nanometer of the particles. And I think that can also apply to the active material.
Thanks, Annika. I'm going to stay with you for the next one. Does the twin screw extrusion work for sodium cathode based materials? They also add that these materials usually result in slurry gelation during the coating process.
I think it could, but I'm just aware of twin screw extruders used for 3D printable sodium-ion batteries. There you use the twin screw mixer to make the compounds and 3D printable strands. But I think in principle it could be also used for sodium-ion batteries. I see no reason why not.
Super. There's another question as well on extrusion relating to the residence time for fibrillating PTFE with a twin screw extruder.
So typically the residence time of the material in twin screw extruders range from about 10 seconds to 5 minutes, but that's extreme. The normal residence time is about 1 minute, and that's sufficient for fibrillation. You, however, can speed it up and have shorter residence times if you increase the temperature, because that speeds up fibrillation of PTFE.
Awesome, thank you. Alan, I'm going to come to you for the next one. What is the detection principle in mass profilometry? How does it distinguish between thickness variations and porosity variations?
A very good question. Thank you very much, Kyle. The principle behind the technology is based on X-ray absorption. X-ray absorption enables one to understand how much mass is present within the detection area. It does not, however, provide specific information on the porosity of the material.
Super, thanks, Alan. We have another question around the footprint of the mass profilometer, specifically here for a 25 centimeter web width.
All right. The model of the mass profilometer that you've seen in this presentation is capable of processing samples with a width of up to 800 millimeters foil. There is no restriction on narrow samples, and one can measure samples as narrow as a few centimeters if that is desired.
And the footprint of that model?
I only have approximate numbers here. Side to side, approximately 1.5 meters.
Super, thanks, Alan. Just coming through, can we integrate the mass profilometry system with an automatic slot die? That's to Alan.
Yes, thank you, Kyle. That is a great question. Absolutely. The system software is capable of exchanging information with a variety of industrial control systems. The data that is produced by the system in real time can be transmitted using industrial protocols like OPC, for example, into a plant control system or into a PLC of the industrial machine. And based on the transmitted variables that could range from an average loading, minimal, maximum loading in a certain area, the machine can make control decisions then to adjust the slot die in order to control coating uniformity.
Thanks, Alan. Can you comment on the resolution and accuracy of a mass profilometer compared to conventional scanning thickness gauge systems?
Yes, absolutely. The spatial resolution of the system is approximately 1 millimeter square. In terms of measurement precision, and we usually refer to precision as a performance characteristic matrix for these type of technology, it's 0.1 gram per square meter or 0.1 plus minus 0.1%, whichever is greater.
And another one on mass profilometry here. What's the mechanism? Does it use a radioactive source?
The technology uses X-ray.
Super, thanks, Al. I'm going to pass to Janam for this next question. Can you further explain how Raman could be used for quantifying non-homogeneity?
Yeah, thanks, Kyle, and thanks for the question. That is a good question. We have worked in the past in looking into quantifying or identifying the non-homogeneity in the slurry process using let's say, for example, a non-contact probe or a contact process probe. And that really gives you a good amount of information on, for example, how is your electrolyte distributed throughout your battery, cathode cell. So what is the gradient? So we have seen in the past where if the slurry is not mixed properly, there is a gradient of electrolyte where on the top or on the surface of the electrode, you will see less electrolyte. And then as you go down inside of the electrode slurry, you see more electrolyte. So all of that is shown in the spectral peaks of the sample, and you will see the intensity of one or more of the compounds peak increasing as that concentration increases or decreasing as the concentration decreases. In a homogeneous sample, you ideally want everything to be the same way. And once you have a streamlined process, you can actually develop a chemometric model that can, basically tell you the concentrations of each of the analytes at various different, sampling point that you're measuring.
Thank you, Janam. We have two questions on the same topic here about the maximum web width for mass profilometry. One asks, can you go widths beyond 1200 millimeters? And another asks, can we go for widths beyond 800 millimeters? I can take this one, Alan. I don't know if you want to, but yes.
Go ahead,
In principle, yes, we can go to any width. I think we're always keen to work with partners and engineer a system to any size. Send us your details. We'd be happy to chat to you about that. I'm going to go to another question here. It's around the Raman Oh, it's disappeared. It's around Raman again, Janam. The spectra you shared are measured with no specific laser power. It says for LFP and NMC, it's sensible for the laser power. Oh, I'm sorry, I can't interpret the final part of that question. I'll come back to that one.
Yeah, I got the idea there,
You
Kyle.
got that? Would you
So
like to maybe frame the
sure.
questions or?
Yeah, so the idea, the question here is that LFP and NMC could be sensible to the laser power or sensitive to the laser power. Their structure could change as the as the laser interacts with the sample. So that's a good question, and yes, we have seen that. So thank you for pointing that out. The spectrometer comes with tunable laser, so you can, for example, tune the laser power anywhere between 50 milliwatt to 450 milliwatt. So the spectral data that you had seen there was taken at about 200 to 300 milliwatt range. But again, depending upon the sample, depending upon how long the laser is interacting with the active material or LFP there, you can always tune the laser to get the spectra the way that you do not destroy the sample or change the structure.
Thanks, Janam. I'm going to come to you next, Annika. One of our attendees has asked a couple of questions on the same topic, so I'm going to concatenate them. So, for the twin screw extrusion, what's the chances of avoiding bubbles? Normally, a vacuum will be there in planetary mixes to avoid these. And then the follow-on question for that is, how do you restrict one part of the slurry not to contaminate the other part of the slurry, which is slightly ahead?
Okay, for the first question, you can also apply a vacuum to the extruder barrel. If you remember the extruder screws that I've shown, the rotating screws, and I talked about the venting at the end shortly before the die. At that point, you can also apply a vacuum stack connected to a vacuum pump and then degas the whole barrel. And with that, we achieve quite good results in getting rid of the bubbles. For the second question, I think the question is how to change from one sample to the next in the extruder. So there are two options. One is if you need it really, very clean, then you would disassemble the extruder, clean it, reassemble it, and start the next formulation. And that takes about 20 minutes in a small lab scale extruder. Another thing what you could do is just purge the extruder, so purge out the old sample with a new, but that requires more sample and quite some time. So usually you have then a smearing of the old sample into the new one for about 5 to 10 minutes. And after that, you should be able to get out of the extruder the new formulation.
Fabulous.
I hope that answers the question.
I hope it does too. Yeah, very clear. Another follow-on question there is, do we see metallic contamination for dry mixing processes?
Yeah, a very frequently asked question. Currently, I have samples for ICP OES to check this. At least we did not see any failure or any problems in our electrode so far. But I hope in a couple of weeks I can answer that question with some numbers of how much ppm I really have then in my product after extrusion.
Fabulous, thank you. There's another question. What's the smallest batch size that you would consider for the twin screw extrusion that fits within a glove box?
Yeah, that's the 11 millimeter twin screw extruder. And there you can start for continuous production, I would say, with about 50 milliliters of sample in powder. However, I used the extruder also as a batch mixer by just dosing 5 grams manually into the extruder barrel, and I had a loss of less than 10% of that sample on the screw. Yeah, so very little quantity.
What about, again, staying with yourself, Annika, what about CNT and silicone rich, so greater than 13% of the anode materials? How do they react in a twin screw environment?
I personally have not used CNTs yet, but we have customers that do. At least they are satisfied with the dispersion of the CNTs achieved. Yeah, can't say more about that. On silicon-rich material, yeah, we have a project together with the university in Braunschweig, with the Institute of IPAT, and they produce silicon-rich anodes for about 4 years now with the extruder, and works quite well.
Super, thank you. And looking like maybe the final question we'll answer, so I'll pass to Janam. Does the Raman spectrometer you shared use standard thread sizes to integrate into non-Thermo Fisher tools there, Janam?
Yes, so another good question. The threaded ball probe that I talked about is compatible with any Dynesco thread, similar to that of pressure sensors that you use for the extrusions or extruders. But Thermo Fisher can also customize the probe and the thread size and type of threads to fit any specific application that you may have.
Thank you. And the final one was a comment from Mahmoud. Thermo Fisher has unique electron microscopy instruments. Who should I reach out to speak to them about? Don't worry, Mahmoud. We've got your details. We'll ensure somebody reaches out to you. So with that, I'd like to again thank Volta Foundation for hosting us today, and Myra for the phenomenal organization and support, and all of the attendants for your sustained attention and interaction in the Q&A section. So thank you.
Yeah. Thank you guys so much. Incredible, incredible discussion. And yeah, over 40 questions. I love it. Great discussions. For those of you in the audience, so hundreds of people in the audience, if you weren't able to access the resources today, please follow up. You can reach me, Myra, at volta.foundation. Happy to connect you to the Thermo Fisher team. Just let me know and we'll get you all the resources you need. There will be a catch the replay coming out within a couple of days for the webinar recording as well. So please rewatch, share with your team, share with your network. And thank you everyone for joining in today. Excited to see you all at the next event.
Thank you.
All right. Bye everyone.
Thank you very much.